Okay, we're going to look at a couple of questions that involve math on the 4.1, chapter 4.1, section assessment. This is on page 103. And number 6 in that question says that the range of most atoms' radii range from 5 times 10 to the negative 11th meters to 2 times 10 to the minus 10th meters. And you need to express these radii in nanometers. So what we need to do is make a conversion factor. And what we have to remember is that 1 nanometer equals 10 to the minus 9th meters. So we're saying that a nanometer is a billionth, okay, this is a billionth of a meter. Or we also can say that there are 10 to the 9th nanometers in 1 meter, or 1 billion nanometers in 1 meter. So if we're starting with 5 times 10 to the minus 11th meters, we want to convert to nanometers. So nanometers goes in the numerator and meters goes in the denominator of the conversion factor. There are 10 to the 9th nanometers in 1 meter. So our problem becomes 5 times 10 to the minus 11th times 10 to the 9th. And so when we multiply exponents, we are adding them. So we're simply adding minus 11 plus 9, and that equals negative 2. So we end up with 5 times 10 to the minus 2 nanometers, which equals 0.05 nanometers. Okay. 2 times 10 to the minus 10th meters converted to nanometers would use the same conversion factor, 10 to the 9th nanometers in 1 meter. And this problem becomes 2 times 10 to the minus 10th times 10 to the 9th. Again, when we're multiplying exponents, we're adding. So we have minus 10 plus 9, which is negative 1. So this ends up being 2 times 10 to the negative 1st nanometers, which equals 0.2 nanometers. So the range of most atoms' radii go from 0.05 nanometers up to 0.2 nanometers. And when we look back here in scientific notation at their sizes in meters, we look at their exponents, okay? And notice that the more negative the exponent over here, the smaller the number, okay? The less negative the exponent, because minus 10 is a little bigger than minus 11, then the bigger the number. So our range is 0.05 nanometers up to 0.2 nanometers. That's why when we're talking about working with things on the atom scale, making materials with things that are atom size, we call that nanotechnology. That prefix nano refers to that billionth of a meter size, which is around atom size. Okay. Number 7 says that if we have 63.5 grams of copper, that contains 6.02 times 10 to the 23rd atoms. Well, how many grams would 1 atom of copper contain? So we'll start with what we have. We have 1 atom of copper. And what we want to do is convert 1 atom of copper to grams. So we need a conversion factor in order to do that. So we need grams here in the numerator, and since we want atoms to cancel out, atoms goes here in the denominator. Well, what can we possibly use here? Well, we can use our beginning information, our given information, which is right here. We know that in 63.5 grams, there are 6.02 times 10 to the 23rd. I had to squeeze that in and write 6.02 E23, like you'd see it in your calculator. Okay, and this problem becomes really 63.5 divided by 6.02 times 10 to the 23rd. And this is 1.05 times 10 to the minus 22nd grams. Does that make sense? It should. We're talking about the mass of one teeny tiny little atom. So it has to be a very, very small fraction of a gram.